Hi, Dr. Revis here with Watch Me Work It. Reduction chemistry, identifying oxidation and reduction species. In Redox chemistry, that is oxidation and reduction chemistry, there are generally three types of questions that frequently get asked. One, which element or species was or is oxidized, and which was or is reduced? Two, how many electrons were involved in the redox process? Redox involves movement of electrons and change in the oxidation state. Number three, what is the oxidizing and reducing agent? So we're going to address these three questions in this Watch Me Work It. So here we go. In this first set, we're going to look at redox chemistry involving single displacement or single replacement reactions. And here's the reaction we have. So let's get going. In order to do a reaction involving redox, we have to first know the oxidation states. The easiest ones to assign are the ones in an elemental state, and they're always zero. And then we assign the rest by standard methods. If you're not familiar with how to do this, watch some of my other videos, and we'll show you how to do that as well. But here we've assigned the oxidation states, and now we look at the transfer or movement of electrons. In this case, we're going to look at carbon change. Carbon we're going to start with. Carbon change from a 0 to a +4. It became more positive, therefore more positive direction means oxidation, which means it lost electrons. So when you lose electrons, it's oxidation. And we can count the number of electrons lost here. We went from a 0 to +4, and that means that was a 4-electron process there. We'll just write it right here. Next, we take a look at the other species that changed. Copper, in this case, went from a +2 to a 0. It became more negative, therefore it moves more negative. That's called reduction. So we have reduction here, and when reduction, that means we gain electrons. 2 electrons. We had 2 units of carbon, 2 moles, 2 atoms of carbon doing it. So that's 4 electrons. 4 electron oxidation, 4 electron reduction. Then we like to know which is the oxidizing or reducing agent. Well, in the case of carbon, carbon was oxidized. Therefore, carbon equals the reducing agent because it was oxidized. Copper was reduced. Therefore, copper is the oxidizing agent. In other words, in this case, it's not just copper, but it's copper to oxide is the full oxidizing agent. Even though the species copper is responsible for the event, to identify the oxidizing agent, we frequently or typically or most of the time tell you the entire reactant. Okay. By the way, occasionally the term reactant and reagent are used interchangeably, and you will hear me doing that. So let's just a quick review on this one. We went from 0 to +4 for carbon. That's oxidation, 4 electrons involved, and carbon is the reducing agent. And we also have copper to oxide, which is the oxidizing agent because copper itself underwent a reduction. Let's move on to the next one. This next single displacement reaction. Let's just assign these as zeros because they're easy to do because they're in their natural state. This is -1. So this is a +1. This is -1. And this is a +1. If we check the sequence of reactions for this as well, I'm going to clear a little bit of a space here now for that. Okay. So if we check the sequence of events here, we see that in the case of chlorine became more negative. Therefore, that is reduction. And that reduction involved a total of 2 electrons, because it's 2 times 1 electron for 2 electrons. Here we have bromine went from a -1 to 0. That's more positive. Therefore, that's oxidation. Oxidation. So we lost electrons, and we lost this 2-electron process because we have 2 times 1 electron here. So if this is oxidation occurring from bromine, then KBr, let me clean that up just a little bit for you. Probably not much, but a little bit. Oh, there we go. KBr is the reducing agent because the species within it was oxidized. So here we go chlorine here, then Cl2 equals the oxidizing agent or reagent or reactant in this case. All right, let's move up to another set. Here we have synthesis, a combination, and a decomp reaction. The first one's a synthesis. So this is a synthesis reaction here, and this is a decomposition reaction here. So let's just do this one. First thing for all of them is sign the charge. You know the routine now. +1. So we went from sodium became more positive here. So this is oxidation. A total of, we went from +1. That's 2 electrons total here. Chlorine underwent reduction. We became more negative. Total of 2 electrons here also. 1 electron times the number of atoms that did it gives you 2 electrons. This is the oxidizing agent here. And meaning sodium. Oh, excuse me, not, yeah. Nope, not sodium. Fluorine is the oxidizing agent, and sodium is the reducing agent. Okay, I think we'll clean that up for you. Let's check the next one in this decomp. Here we have, I always get like to sign these because they're easy to identify. So this is a -2, this is a +3. So here we became from here to here, we became more positive. Let me just for consistency keep you so you can see it later. We became more positive here, so that's oxidation by number of electrons there. So -2 there. That's 2 is 4. Looks like 4 electrons. Assuming no math mistakes here on my part. Let's say 4 electrons here. Nope. We have 3 times here. So nope, not 4. Let's do it again. We have 6 times 2. Total of 12 electrons. So we have 3 times 2 times 2. Now I can even do that math. 12 electrons. There we go. So now we have boron, and this is, watch me work it. So here we go, boron. We have here, we went to more negative. More negative means reduction. We gain electrons in reduction. We lose electrons in oxidation. What's oxidized becomes the reducing agent. What is reduced is the oxidizing agent. It caused the other species to be oxidized, and we check our electron balance, 12 electrons here as well. So you just do the same type of math there as well. Let's do another one here. This is a combustion reaction. And we have it written here as H4C, only for those who might not be aware. The organic chemists write it like this. But I did this just for consistency. So this is a -4, this is +1. On hydrogen, that's balanced. This is 0, -2, +4 in that carbon. So there's no real change in that carbon. Let me clean this up so you know what that is. That's a 1. And here we have a -2 and a +1 here as well. So what we have happening here is we have copper becoming more positive here, and that's oxidation. Okay, and so we have oxidation going here from a -4 to a +4. That's a total of, it's like a number line. So you count it as a number line. That's a total of 8 electrons involved there. And here we have, must have reduction. And you can go to either one of these. I'll just take it to the water on the outside. So if we go here, we basically have -2 electrons here on the oxygen, and look like 8 electrons, that's right. So we have 2 here, there, so we get our total of our electron count works out there. So we have reduction. We have reduction here, and therefore we this is your oxidizing agent. And this is your reducing agent. Make sure you check your count. That's what I'm doing now on everything here. Yep, so we're good there. 2 times 2 times 2. Yep, that works out for what we need to do here. Yep, we check the count over here, and that works out. Yep, 2, 4 plus 2. There we go. Times 2. Got the numbers worked out. All right. So that's how we do the combustion analysis as well. Now let me just take 2 more here just for a little bit of a slightly different view of it, so you can be aware of this when you do redox chemistry. This is slightly more complicated. It's really not. It's just different features you have to watch for in it. And so that's why I want to work this one. In this particular case, we just want to see how it works out when you have something a little bit more complicated to play with. So in the case here, we're going to do every one of these. So this is -2, so SO4 itself is -2. 10 must be a +2 here, and for this to balance out, this must be a +6 here. And so on this side, we have again -2. We have 0 here, of course, and so here this is +2. So for 10 again here, and so now in this particular case, to balance out, we know this must be +4. 3 times 2, yep, +4. So we go here, and so we get a change here, sulfur as a reduction. So let me just be consistent with the way we've been presenting it. Just do this. So this is going to be reduced here, and this is going to be oxidized. So this is oxidized, and this is reduced. And then you do the rest of whatever math you want to do here as well. So that's reduction. So this is the oxidizing agent. Boy, that writing's getting really horrible, isn't it? Let me just clean this up a little bit for you. This is reduction. Not much better. And here we have oxidation. Oxidizing agent, not oxidation. Okay. The oxidizing agent. There we go. We got it out. and this is the reducing agent. Okay. In other words, this is both the oxidizing and reducing agent. Just one more here. We do this one, we have a -2 here, and we have, this is, zinc must be a +2. So for us to work out, this must be a +4. And so here, carbon, here's a +4 also. So -2, here's a -2, and this is a +2. And if we look at this, boy, there's no redox. Okay, because nothing changed. All right, there you have it. How to assign charges and determine oxidation and reduction.